In this lecture, we will discuss Chapter 14, Sound. We will learn all about sound waves, how it is generated, how it is transferred. We will learn about longitudinal waves. We will learn about standing waves, about the musical instruments, and few exciting applications. So let's start. When you see lighting during the rainy season, the distance between the lighting and your location can be calculated easily. All what you have to do is just count the number of seconds between the moment you see the flash and the moment you hear the thunder. Then multiply the time, the number of seconds, by the speed of sound, which is 345 meters per second. This will give you the distance between your location and the location of the lightning. We are all familiar with this image. In order to produce sound, the player needs to move one of the strings and let go. As it let go, as it try to restrain to its unrestrained position, it will start vibrating, oscillating. So in order to generate any sound, musical or otherwise, you need to have a vibrating source. For musical instruments, sound waves are created by several ways. For guitar, for violin, it is by the oscillation of the strings. For clarinet, by vibrating reed. For the drum, sound is produced through vibrations of the drum head. For the piano, similar to the guitar and violin, you are talking about the vibration of strings. For a singer, the sound waves are created by the vocal cords. The vibration of the vocal cords and the vocal cavity produces the sound waves. In order to understand the mechanism of sound waves, let us consider this tuning fork. If you knock the tuning fork here, the end of the fork will start vibrating, trying to come back to its original position. As it vibrates, it acts on the air molecule in this region. It applies higher pressure on the air molecules. This generates a compression. As it tries to return back, this generates a low density region. The air molecules now will have less pressure on them. We call this refraction. So as the tuning fork vibrates back and forth, it vibrates between compressions and refractions. And sound waves that are created are just a stream of compressions and refractions. In this image, we see such a stream. Here, these are compressions. This is compression. This is compression. This is also compression. Between them, this is a refraction region, another refraction region, a third refraction region, and so on and so forth. So the mechanism to produce sound waves in air here simply it depends on changing the pressure of air, and this way the variation in the pressure can be modeled by this sine function. The pressure is highest in the compression region and is lowest in the refraction region. The variations in the pressure represents the oscillations of the tuning fork. These compressions and refractions, when they hit our eardrums, the eardrum will respond to them. If there is a compression, the eardrum will go inward. If there is a refraction, the eardrum will go outward. So the eardrum will start vibrating in and out, and this way the sound is transferred to the humans because the eardrum is connected through a mechanism which we will learn about later in this lecture. And through that mechanism, the audio nerve takes the message and sends it to the brain. When you have a stream of compressions and refractions like this, we call this longitudinal waves. Longitudinal waves. There are three categories of sound waves. The first category is the audible waves, which is generated by the compression and refractions. And here, the range of wave frequencies is between 20 and 20,000 hertz. This is the audio spectrum. Any frequency in this range can be heard by the eardrum of humans and analyzed and sent to the brain. The second category is the infrasonic waves. Here we are talking about longitudinal waves with frequencies below the audible range. For example, earthquake waves. Here, the frequency, we cannot hear it because it's lower than the limit for hearing, the 20 hertz limit. The third category is the ultrasonic waves. Here, longitudinal waves with frequencies of the audio range. So ultrasonic means frequencies higher than 20 kilohertz. So we cannot hear it, but there are animals like dogs, for example, that can hear such frequencies. For example, there are certain whistles that can generate sounds, ultrasonic waves, with frequency higher than 20 kilohertz. In order to generate ultrasound, we may use a crystal and apply electric voltage on the two sides of the crystal. As you can see here, we have electric connections. The crystal may be made of quartz or strontium titanate, special type of crystals that respond to the electric voltage. And if the electric voltage is oscillating, alternating current, it oscillates accordingly with the same frequency of the applied voltage. So this way, we can generate the desired value, the desired frequency using this crystal by controlling the frequency of the applied alternating current. This phenomena of transforming electrical energy into mechanical energy, sound waves, mechanical energy, is called the piezoelectric effect. In general, when we use ultrasound waves, the waves, as it penetrates a medium, when the medium density changes, the waves, part of it will be reflected and the other part will be transmitted. The percentage of the reflected portion can be determined from this formula. Density of the medium where the wave was incident minus density of the new medium divided by summation of the two densities squared. So any variation in density in the medium can be sensed using ultrasound waves. There are many exciting and important applications for this phenomenon. For example, ultrasound waves are used usually to observe fetuses. So we use ultrasound source, probe, electrode, and the ultrasound waves reflects partially from the fetus, and wherever there is change in the density, there will be a new reflection. Usually the reflected back sound waves are recorded, taken back to the computer screen, and this way we can see the details of the image of the fetus. There are many other exciting applications for ultrasound, like the CUSA, Cavitron Ultrasonic Surgical Aspirator. And this device allows surgeons to remove brain tumors. Another application using ultrasound with 23 kilohertz and at the tip, it's possible to shatter the tumor into tiny pieces and can be sucked up. Other similar applications for ultrasound in surgery to destroy uterine fibroids and also tumors of the prostate gland. Ultrasound waves are also used to break up kidney stones that otherwise too large to pass. Other applications that use the energy carried by the ultrasound waves is the high intensity focused ultrasound technique, HIFU as it is known. It is used in the treatment of Parkinson's disease to remove the damaged part of the brain that caused this disease. Also in strokes and in targeting the delivery of therapeutic drugs in a specific brain locations that are hard to reach. It is also used to measure distance between the camera and the object to be photographed.